Welcome to Higher Structures seminar series of Feza Gürsey Center for Physics and Mathematics. This is our fourth year in our seminar series, and the first talk will be given by Doğancan Karabaş. He will tell us about a computational approach to the homotopy theory of DG categories, and we thank Doğancan for agreeing to give the first talk. Please.
I thank you for inviting me. Thank you very much. So, as the title say, I will tell you a computational approach to the homotopy theory of the DG categories. And for that, I don't know how much the audience know about this stuff. So I will quickly tell what I mean by these keywords. Actually, I won't quickly tell what homotopy theory means, but let me just say this differential graded and also I set my notation by doing this differential graded category. So basically it's DG category. It is a category, see, where the morphism space so between two objects is not just a set, but it is a chain complex of K modules. Sorry. And K here is commutative ring. So whatever the things I will tell holds for all commutative rings. But I will set for simplicity K equals just Z2 so that I don't deal with signs. So this means basically for each morphism, so there is a grading of it. They are graded. And they have a differential. And these are my notation for them. And DG functor is a functor preserving grading and differential of this morphism. Maybe I didn't say, but it's written there. This is the joint work with Sanjin Lee. And we have two papers on this. And one is the recent one. And okay, so now I tell you DG cat. DG cat is a category. So objects are DG categories. And morphisms are DG functors. So category of DG categories, basically. And this is the main thing I'm trying to understand here, DG cat. But not DG cat, the homotopy theory of DG cat. So that will be the aim. So before proceeding, a little bit geometry here. So why, let's say, a symplectic geometer, I am a symplectic geometer, interested in these DG categories. So why a symplectic geometer care of this? So one is this thing. This is Kontsevich-Koshev conjecture. So but before saying that, let me put it down. Say this. So let's say I have a symplectic manifold, and then there's an invariant associated to it. It is called Fukaya category, or here I will work with Rab Fukaya category of this. So this is an actually A infinity category, naturally. But any A infinity category can be is equivalent to a DG category. So there's also DG model for this. It's a category. Its objects are Lagrangian submanifolds. Morphisms are their intersections, kind of. And the operations coming from counting pseudo-holomorphic disks. I mean, no need to go in details, but it's very complicated invariant. And it knows a lot of symplectic manifolds. And maybe let's put this too. And it's one of the most, I mean, first, we are interested in this invariant because it tells a lot about symplectic manifold. And second, there's a homological mirror symmetry conjecture. Saying that for a symplectic manifold M, and there is a algebraic variety for simplicity, let's just say right now this. And this Fukaya category or Fukaya category of this thing, you have this W in parentheses. There are many versions of Fukaya categories. Is equivalent to coherent sheaves, category of coherent sheaves on this algebraic variety. This is called mirror symmetry. And this is a conjecture, but we are trying to understand that. So this invariant is key to approach this conjecture. And second is Kontsevich-Koshev conjecture, but this is actually proven now. Proven by Natter Zaslow and Ganat Pardon Shende. So it says that for a symplectic manifold, Weinstein manifold, and Weinstein manifolds are symplectic manifolds, which are non-compact, equipped with Liouville vector field, uh, escaping infinity, and has nice singularities. The Liouville vector field has nice singularities. So This is is there a question? By the way, you can stop me anytime.
Can I ask one question about Fukaya category? It's about, yeah, I mean, you said that this is an invariant of the symplectic manifold M. So suppose that I have two symplectic manifolds whose wrapped Fukaya categories are equivalent. So these symplectic manifolds are related to each other.
Not necessarily.
I
So
see.
sometimes it is not even distinguished topology. So
Oh,
it's
I
not
see.
even complete detect topology.
Oh, okay.
I can, for example, T star R and T star R2 are two symplectic manifolds, and their rep categories are the same. So even doesn't the dimension even is not it doesn't even detect dimension. But in certain cases, it's very strong. So if you give some assumptions on your manifold, symplectic manifolds, they turn out to be very strong. For example, this symplectic manifolds we say subcritical. Uh, so I mean there is some classification, and this is actually when it works, it's very strong. Let's say,
I see.
uh,
Okay. Yeah, thank you.
not that general. Okay, so okay, Weinstein manifolds. I just give definitions vaguely because I don't want to spend too much time, but let me give you an example and tell you what this conservative conjecture is. Example is the cotangent bundles. Cotangent bundles. Let's say T star S1. T star S1. The cotangent bundle S1. And the level vector field. And this is equipped with level vector field, which is this red one. And when you retract level vector field back, you end up with some subspace of your symplectic manifold. That's called skeleton of it. So for example, here, the level vector field goes to infinity, but if you go back, you actually come back to zero section. So the zero section is called skeleton. This is skeleton of T star S1, which is zero section S1. So the skeleton of M is uh, defined as like retract via level vector field. And another example is there's a pair of pens. This is also a Weinstein manifold with this level vector field. Let me make it. And if you retract this one back, like you get this kind of singular subspace, which is the skeleton. So each Weinstein manifold comes with a possibly singular skeleton. And then this Kashif conjecture is, and the other examples of are, let's say, uh, like Stein manifolds, if you know, uh, uh, affine varieties, smooth affine varieties. And Kashif conjecture says that Ref category of this W is given by microlocal shift category. This is a microlocal. It's like called DG category of microlocal shifts. On the skeleton. So it's some shift category attached to the skeleton. And let's call it X. And let me call X as the skeleton of W. So this is proven. So instead of actually dealing with this Lagrangians, we can just focus on the skeleton of your manifold and just look at microlocal shifts on it. And moreover, this microlocal shift, this is a co-shift of DG categories. What does that mean? It means, let's say your skeleton X, let's say it has two pieces, X1 and X2. Let's say an open covering of your skeleton. Then the microlocal shifts on X can be category, I mean DG category of microlocal shifts on X given by homotopy colimit. This is homotopy colimit of microlocal shifts on X1 and X2, and you glue them basically. So there's a gluing formula. So you can compute microlocal shifts locally, then you can glue them. But this gluing is not like shift, this is co-shift. In shift language, normally gluing is limit. Therefore, here is gluing a colimit, and there's also ho here. And I will talk about that, homotopy colimit. And this formula basically tells that you can compute square categories local to global way. And each piece, for example, in this skeleton, you can just look at the neighborhood of the singularity and compute some micro shift category, whatever that means, here, and the other side, and then you glue them. So, okay, let me finish this geometry part by saying that there's a result by Nadler. And he says that for any skeleton, this is skeleton, there is a partition, this finite partition, such that after deformation, maybe, let's say, this, whatever, these are not that important, but so there's a partition such that the microlocal shift category on each piece is given by maybe in parentheses pre-triangulated closure of all equal signs. Let's make it, of course, equivalence closure of uh, a quiver seen as a DG category. So it says that when you have some skeleton, you can decompose it in pieces such that each piece on microshifts on each piece is just given by a quiver. For example, microshifts on this singularity is given by A2 quiver, this quiver. How do I read quiver as a DG category? I just take all arrows are degree zero, differentials are zero, and there are two objects, one arrow. It's like I can see this as a category like that. Like vertices are objects and arrows are morphisms. And I can freely compose them if there's compositions. So in short, if I can glue DG categories via homotopy limit, I can compute Fukaya categories, which is a great for simplex geometry. So gluing, but how do I glue DG categories? How do I do operations with DG categories? That's the question. To do that, we need to understand the homotopy theory of DG categories. And we need to understand the constructions like homotopy limit, etc. Because now we know the pieces are just will be quiver. Pieces are easy. Just gluing is hard. How do we glue? So anyway, this was maybe longer than I expected introduction. And now, if you don't care about this, okay, but this is my starting point of my interest. Now, think like this is a new start. Now, it will be category theory. So now, I want to remark this first. All equivalences here are not isomorphism. They are quasi-equivalence. So above this is a quasi-equivalence. And quasi-equivalence, let's say F from C to D is a quasi-equivalence if F is quasi-essentially surjective. That means for all objects X inside C, Fx, sorry, for all Y in object D, that exists an object in C such that Fx and Fy, Fx and Y homotopy equivalent. They are isomorphic up to some differential. It's not a strict isomorphism. And if it's quasi full and faithful, that means for all x prime inside objects of C, the F restricted to this morphism space, a chain map between morphism space, and this is a quasi-equivalence, a quasi-isomorphism. So it induces isomorphism on the homologies of the chain complex. So we are interested in DG categories up to quasi-equivalences. So DG cat, we are not interested in this category of DG categories and DG functors. We are interested in DG category, DG cat, where the quasi-equivalences are inverted. So we want to invert quasi-equivalences. And I call it the homotopy category of DG categories. This is called whole DG cat. Homotopy category of DG categories. So what does this mean? So this means The quasi-equivalences are not isomorphisms in DGCAT normally. So a quasi-equivalence doesn't need to be isomorphism. It doesn't need to be invertible. But we want them to be invertible. We want them to be isomorphism. We want them to be our notion of isomorphism. So what we do, we add the inverse ourselves to the category. So we localize. This is called localization. We localize the category. But the problem is when you localize a category, it really completely, not completely, but it will really change. It's not, I mean, DGCAT and this whole DGCAT are very different things. So an example is this. Let's say I am in a let's say DGCAT just consists of three DG categories. Just there are, just assume it's not true, but just there are three DG categories. And let's say only DG functors are this. These are the only DG functors. This is the quasi-equivalence, let's say. This is quasi-equivalence. So in such world, let's say what is home from C to C? I mean, what are the morphisms from or functors from C to C? I didn't draw here, but there are identity functors, and they're multiple, so it's just K times identity, like K. One dimensional, basically. Just identity, because if you look, there's no other arrow starting from C and ending in C. So I can, let's say, compose the DG functors. I can compose this with this, but I get this. I don't get any functor from C to C here. Just the identity functor, which I didn't draw here. So one dimensional home space C has. And let's say, now invert quasi-equivalences. What happens, let's say? So inverting is a process where you add the inverse of that arrow, although actually there's no inverse. So you artificially add this inverse. So, but when you add that, now look at the home from C to C. I mean, I can compose now these three arrows, and there is a new functor, artificial functor. It's like a quasi-functor from C to C. And I can actually do one more round. 2, 3. I can just continue composing these three arrows many times, and I get so infinitely many arrows. So now this is infinite dimensional, this space. Infinite dimensional. So home space changed drastically from one dimension to infinite dimension. So therefore, localization changed the category a lot. So then what is our goal? Goal, understand this new category, whole DGCAT, where the quasi-constants are inverted via DGCAT, via the original category, which means understand morphism spaces, colimits, etc. in DGCAT via DGCAT, via morphism space colimits in DGCAT. So basically we want to find a link between this old one and the new one. And how can I get this from just looking here? looking at here. And there is a method, there is a way to approach this problem via cylinders. So these are main methods, cylinders. One can approach this problem via introducing cylinders. So now I will give you an example from topology, and then I will make an analogy to DG setting, and I will show our result. So example from topology. So let's say top is category of topological spaces. Okay. And homotop is basically this topological space, but this time weak homotopy equivalences are inverted. Actually, this is the classical example. This is how homotopy theory actually arrives. This setting. So basically, I will take the category of topological spaces and I will invert weak homotopy equivalences. I will make them invertible. Normally, they don't need to be invertible. They don't need to have a continuous inverse. So an example is, but before this, maybe let me stop and any question you have so far. So
DG categories are related with non-commutative schemes or varieties, right?
as a coherent shapes, or as we can associate it categories to such varieties, and those are DG categories also, yes. So there's an
Uh,
algebraic, yeah, yes.
the algebraic version of this is this theory is like considering non-commutative schemes kind of thing.
And so through, I mean, non-commutative schemes, you can think as a DG categories.
Right.
So yes, you can think like that.
So
Uh,
all DG
because there's
categories,
not always geometric model for them. So you think like DG.
I see. So
Yeah.
okay, yeah, thank
Okay.
you.
So yeah, DG categories are, I just taught symplectic geometry side, but um, actually there are much more motivation from algebraic geometry than symplectic geometry, of course. Okay, so then I can give you examples. First example is, let's say, I will call our home is home in this homotopy category. So here also I should call it our home, let's say, okay? This is derived morphism space. Derived, I mean, you can also think derived. Derived means actually after localization, if you can, I mean, not in this context, I mean, in that way. So derived means after localization in new category, the homomorphism space becomes this. So this is derived morphisms. Derived home, our home. So let's say, and home is morphisms in just the original topological top. So let's say X is CW complex and Y is a just topological space. And let's say I want to understand morphisms from X to Y after we invert stuff. Because there are new morphism arrays. There are not just continuous maps. There are some new quasi-morphisms. And this is equal to, I'm giving the result. This is not equal to just morphism from X to Y, because X is CW complex. There, we have this, but we identify some morphisms. So just continuous maps from X to Y, but up to something, and that's up to homotopy basically. And what is homotopy? Let's say I have two continuous map F and G. I say F and G are homotopic if there is this diagram. There exists H, continuous map H, such that this commutes. This the typical homotopy definition that everyone knows from undergrad maybe. This F and G are homotopic if this I1 and I2 are just inclusions, and the X times I is interval here. So X times interval. So this is actually what? This is a cylinder for X. So I take X and I multiply by interval. I make a cylinder of X. It's not like a cylinder of circle, but. And using that, I give this being homotopy, what this means, basically. So this gives me like homotopy. So basically, the takeaway here is I can describe our home using usual home using the cylinder object, by this. So I use cylinder object to define it. Of course, cylinders in topology are cylinders. So I will make analogy later, but this is just cylinder. So so as I show now, we can understand this in topology, our homes. What about, let's say, colimits? What happens to colimits in homotop in the after you invert this? Colimit in topology is just gluing. For example, look at this gluing. Look at this the colimit. This is a diagram of D2s and S1. D2 are disk. They are disk. S1 is circle. And this says colimit means glue, basically. It says glue two disks in such a way that you identify the images of these two arrows. And this arrow assume that it hits the boundary of these disks. So basically, this column says that you need to glue two disks along their boundaries. What do you get? A sphere. You get sphere. This is colimit in topology, in category of topological spaces. But let's say if this operation makes sense in homotopy theory of topological spaces, homotopy category of topological spaces, we know that D2 is weak homotopy equivalent to point. Weak homotopy equivalence means there's a map between them which like identifies their homotopy groups. So the homotopy groups are same, and the usual inclusion gives the weak homotopy equivalence between them. This can, or you can think like retract. You can retract D2 to point. So they are weak homotopy equivalent. So if collimate is a sensible operation up to weak homotopy equivalence, then I should able to replace D2s with points. And I should get the same answer up to weak homotopy equivalence. But what do I get when I glue 2 points? The image of S1 is point here and point there. So I just identify 2 points. Becomes 1 point. This is a point. Okay, it can be different, but are they weak homotopy equivalent? No. This one is S2, one is point. You cannot retract S2 to point. And they also groups are different. The homotopy groups are different. So they are not weak homotopy equivalent. So colimit is not a valid operation in here. No homotopy category of topological spaces. So it needs to be replaced. There are different ways to know how to continue from here, but one is like you find the best approximation of colimit. So here, I mean, I define this. This in other approaches, this is not definition, this is a consequence, but I say now I define a homotopic limit, replace it with homotopic limit. And which I will say ho colimit. Ho colimit. Let's say this thing, homotopic colimit of this thing. What do I do? I define it as colimit of, again, using the classical operation. Colimit is in the previous top, not whole top. Of point S1. I take this part of this diagram, but I put in between cylinder of S1. I kind of make gluing relax gluing, not like directly glue. First, I put something in between, then I glue, like relax gluing. So this is cylinder of S1. So whenever you have commutative collimate, you put this thing between. You put something, a cylinder of this thing between. It doesn't need to be S1, whatever. And then you glue. If you glue this, what you get? I'm gluing point, cylinder and point. And I identify this point with this circle. It makes it closes. It makes circle point. And glue this part with point. It also makes it like close. Then the result is you get sphere. If you glue point, cylinder and point, you get this sphere, which match with this. I mean, I should also take homotopic limit here, but if you do, it will still give you S2. So now I get a consistent operation. Homotopic limit is a way to glue things in this homotopy theory. And this, yeah, this is in geometry what I care about, understanding homotopic limits. But this is an example. This is not the DG category setting. This is from topology. So now I tell what we do, essentially. But before that, any question? And just the point of these examples are the operations in homotopic category of topological spaces or whatever space, whatever thing. can be explained through the cylinder thing, some cylinder construction. So in other setting also, I will construct some cylinders. Through that, I will explain all these operations. That's the thing. So cylinder approach. So any question?
So this cylinder approach is a well-known theory in the topological spaces setting, or it's your observation with your coworker.
This is abstracted by Bauer.
I see.
Hans-Joachim Bauer in his algebraic homotopy book,
Oh,
he gave this approach in abstract. So he said, uh, so let's say you have a M with this is a category, and you give cofibrations and cylinders, functorial cylinders. And there are 5 axioms. You give me this thing. You give, of course, what weak equivalences. So things that you want to be inverted. You give me category and things inside which you want to be inverted. And you give me some cofibration. You define cofibration, some maps, special maps, and cylinders. This for each object you define a cylinder, and you show some axioms they satisfy. Then it gives you a way to understand this category via M. So gives tools. And this is called I category structure. He defined this thing on M. So basically, in category of topological spaces, I category structure, cofibrations are relative CW complexes. I kind of ignore that, but cylinders are usual cylinders. With usual cylinders, you have I category structure on category of topological spaces, which makes you helps you understand homotopy theory of topological spaces. And he showed that if you give me I category structure, it gives you cofibration structure. It implies that. This is like half model structure. Cofibration structure basically, uh, if you model structure, model structure idea is also similar. The goal is similar and same. Understanding localization via the original category. You give model structure. But in model structure, you give with weak equivalences W, you give cofibrations, fibrations, and functorial factorizations. Some stuff you give, and what we obtain is half of that because we don't give vibrations. For example, our structure, we are describing half of the structures, constructions in a category, a homotopy category. That means, for example, we describe cofibration structure describes homotopy limits, but it doesn't describe homotopy limits. So it derives, let's say, left tensor product, but not right tensor product. It's always described one and not the other. So it doesn't describe the coversions or describe coversion and not the other. So it's like half model structure. Because when you derive stuff, there is always left derived and right derived. And our structures define left-right things with covariance structure. So that's what we give to DGCAD in our case. We give covariance structure to DGCAD. And one other remark is Tabata actually gave, of course, model structure. Model structure to DGCAD. So why we defining again? But their model structure is good for many purposes, but not good for computations. The thing is, each model structure also gives you a cylinder, if you like. And their cylinder is very complicated. Because if you see here, I describe homotopy collimate through collimate with cylinder. So they also, in practice, with model structure, you also do this. And this cylinder, there's also this cylinder. Or you can resolve the diagram. In both ways, in Tabata model structure is not trivial. You don't know usually how to resolve a diagram. You need to work with that particular diagram and figure it out. Or if you want to put cylinder here, the Tabata cylinder has uncountably many errors. So even if you have your initial category is nice, Tabata's cylinder is very complicated. So that's why we call our approach combinatorial approach, because our cylinder is very nice. And I will show you now how we define the cylinder. So I don't have much time left, so maybe I will show our structure. And again, the motivation here for us is computation of symplectic invariance. So computing is very important. So you give I category structure on DGCAD. As I said, I need to tell what cofibrations are. These are actually similar to Tabata's. So let's say D is a DG category. So I tell you what cofibrations are. So cofibrations are special DG functors that I need to state here. And cofibrations are DG functors such that domain is D and the image can be seen as some extension of D. Extension means you have a DG category, you first add some extra objects to your DG category without connecting them with any other arrows. So I have a DG category, I already have objects and arrows, and I add extra objects in disconnected way. So they are just floating around in your category right now. Then to this new category, I add a morphism, F1. I draw an arrow, F1. So maybe an example, meanwhile, I show with example. Let's say my initial category is this, D is this is D, two objects and one arrow. And then I define a DG functor from that such that it hits itself, that DG functor hits itself, D. But there are more stuff around. First, I may have more objects. Let's say this. I can. And then I have F1. For example, F1 can be morphism from this to this. I can also add morphisms to that picture. So F2 can be morphism here, etc. So add F1, F2. You add in such a way that differential of F1 should be inside morphism space of here. So differential of F1 cannot contain F2. And differential of F2 can contain F1 but cannot contain higher morphisms, etc. It goes like this. And I can add like this is a well-ordered set. So it can be indexed by any ordinal number. So it's like attaching disk.
So you
It's
are
like
doing
actually
some
constructing.
countable process, countable processing.
It doesn't need to be countable.
No need to be countable.
It doesn't need to be countable, yes.
Also, instead of F1, F2, and so on, uh,
So I should not say F1, F2. Maybe it's misleading, but it starts like that. Uh, how to say? It's like transfinite,
okay.
a transfinite process. It doesn't be countable. No, right? So, I mean, it doesn't need to be countable.
So
If
it
you,
will form a well-ordered set, basically.
it's already well said. Indeed, yeah. Yeah, it can be uncovered. So well-ordered set, I mean, true. So positive real numbers are also well-ordered set, which is well-ordered. No, sorry, positive real numbers are not good example. But anyway, but it can be uncountable indeed. Yes. Okay, I don't have much time left, so maybe I tell the cylinder now. So this is how cofibrations are. But one thing is I define cylinders for semi-free DG categories. So semi-free DG categories is it is, let's say C. C is a semi-free DG category if this is a cofibration. Map from empty set to C. Actually, that means C can be obtained from empty set by first adding some objects and then morphisms in this way, like I told you. If a category, I mean, the categories which can be described like that are semi-free DG categories. By the way, I should also say compositions, AIs, FIs are free. So they freely compose. There's no relation between them. So if F1 and F2 compose, they compose. It's not zero. So arrows are free compose with each other with this construction. And semi-free DG category is just there's no D to start with. You just start with adding these red points and then draw some arrows between these red points and adding arrows freely. And then our cylinder for C. So again, C is this, right? C must be of this form. Some objects and some morphisms added in succession. And we call Fi generating morphisms. And the cylinder for C we define as so let's say first C1 and C2 are copies of C. Basically they are C, but I just labeled them C1 and C2. And I take disjoint union of two DG, my initial DG category, C1 and C2, and I now adding them to some morphisms. I add Tx, some new morphism Tx for each x for each object of C, I add a morphism Tx, and I should also say its domain. And so it is from x1 to x2. X1 means the first copy of X in the first copy. X2 means the copy of X in the second copy of the C. And I add TF from X1 to Y2 for each generating morphism F from X to Y in C. So C has generating morphisms, as I told you, the F1, F2, F3. For each of them, I add this new morphism TF from X1, the first copy of X, to Y2, second copy of Y, which is the codomain of this. And such that Tx is degree 0, differential of Tx is 0, degree of Tf is F minus 1, degree of minus 1, and differential of Tf is uh, it is given by it's defined by inductive way. So there's this kind of correction term. I mean, there's this new character TDF, and depending on DF, for example, T0 is 0. If differential 0, that's 0. If this identity is also 0. And this is linearly defined. Means if you sum them, you sum them. If this index here, you sum index, you also sum T characters. And there's a TGF. If I have this composition TGF, how is it defined? It's defined as G2 TF plus TG F1. And using these rules, you can determine what this is, this correction term. And this is our cylinder uh, construction. And also we invert, after that we invert T-axis. And which can be described as a, yeah. We also have description of how we invert them, but plus you invert Tx. You make them invertible arrows. And this is our cylinder construction. As you see, we just add some morphisms depending on the complexity of C, not crazy amount. If you compare with Tabata, it's very crazy. And therefore, when you compute homotopic limit, etc., the computation is very doable. And we apply to this to some like geometric problem and get in result some other results. But I'm already over time, so uh, I should stop here.
May I ask a question?
Yes.
Actually, I couldn't relate why these cylinders in this setting of semi-free categories are maps, but not, for example, lines. I don't know.
So you mean this morphisms?
Yes, the
Which
last
morphism?
example. Yes. Why are they maps, but not like lines or like that?
So what do you mean by line?
I mean, you first give some example, and we talked about these concrete cylinders, like this product of spaces, but and uh, because of that example, I think about lines but not maps. If it,
Okay, good point. Good point. Because that was topology, right? There
Mhm.
are kind of we are connecting with lines, right?
Yes.
Here, this DG categories, of course, we don't have lines. We have is what is line in, so your question is what is line in topology? And what is the line that you see in topology in DG categories? It is invertible map. Yeah,
In
invertible
DG
maps.
categories, lines are maps. Or
Lines are invertible maps. So TX is those
huh.
lines. TX. So let
Okay.
me let me show you quick example, which I already have the picture. So I do shortcut. Uh, where is it? Okay, so this, for example, look at this example. Um, let me clear the area a bit. Maybe this example make it more clear. So say my DJ category is this, okay? My DG category is this thing. C is
Okay.
this. Assume. What does that mean? I have three objects, X, Y, Z. I have a map from X to Y, Y to Z, and X to Z. And let's say differential of H is GF, differential G is 0, DF is 0, and degrees are whatever. And the arrows compose, so GF, there's GF. So let's say you want to make a cylinder of C. So think like topology. How do you make a cylinder normally? If I circle, right? How do you make cylinder?
Uh,
You perk.
yeah, circle times a line.
You can also do that, or you can do like this. First, you put one circle one end, one circle the other end,
Mhm.
then fill the between, right?
Yes.
You can also do that. You do exactly the same thing here. You take your
Hmm.
category C, take your category C, take two copy of it. That's the two copy there. I take two copy. Therefore, I label them X1, Y1 because I make my one circle, two circle, and put to the ends. In category language, take two copies of my category and put two ends. Then I need to fill the between, right? If I now I have think like I have two circles, I need to fill between. What do you do to do that? You need to draw lines, as you said. I need to draw lines from one circle to other, draw lines. So here, lines means I have three objects, I need to connect these three objects. Those are my lines. So this Tx, Ty, Tz. That's the morphism coming from the objects, and they are invertible.
Okay. In
But
DG categories, this setting is in DG categories.
this is in DG categories. In geometry, it is like circle. Like in topology, there's
Okay.
circle. There's circle here, and I draw lines.
Okay.
But actually, I didn't draw all lines, right? I draw a couple of lines. If you can think, because I cannot draw in DG setting all lines all together, infinitely many lines. I draw maybe three lines only.
But we have here three objects.
Yeah, three lines. But if you think like more picturally, in this analogy, maybe instead of infinitely many lines, what can you do? You can put the remaining patch, not line, but like square, rectangles here, right? I can
Yes.
put three lines and then put three rectangles there, right? So those, the other morphism, TF, TG, and TH, are those like the
Yes.
rectangles.
Okay.
So the other ones, these ones, those are like rectangles. These are lines. I draw two lines and I put three rectangles. You can think like this. So I can construct a topological cylinder like that, right? Two circle, three line, and three rectangle.
Okay.
So it's similar analogy, but problem in, sorry, I'm very over time with my discussions, but
That's fine.
the problem with DG, thank you. The problem in DG setting is, we know in this kind of settings, you usually need higher and higher things. You can also think in the topology. This is one-dimensional example, of course, circle. Think like it's higher dimensional. What do you do? Then you need to add not just rectangles, then you add cubes, those things. So it's like homotopy theory like this. You add homotopy kind of here corresponds to rectangles, right? Then you add homotopy of homotopies, which corresponds to cubes. Then those things. Normally you expect that kind of infinitely many addition. Normally you add infinitely many homotopies. You expect that. That's what happening in Tabata setting is even not that. It's much more complicated than even that. But that's what would you expect from the cylinder object, having infinitely many arrows there. But that's what our work shows. We show that only rectangles are enough, which makes it finite dimensional. Finitely many arrows you add. If your initial category has finitely many arrows, you don't need to have infinitely many arrows. That allows the path of computation or combinatorics in symplectic geometry. That's our result, actually.
Doğancan, there is a question in the chat box
Yeah.
by
Is
Van
there
Wei.
Okay, is there some example that your construction recover previously already existed cylinder objects? So the thing is, our cylinder object is are quasi equivalent to them. Any cylinder, any cylinder object, but ours is much simpler. So the cylinder objects so far existed are much more complicated than ours. So maybe in linear case, I don't know, but if there is this linear case, if your category is this way, I think our result is kind of known, maybe not explicitly, but implicitly, if your category is like this. If your arrows are not forming a loop, let's say, as soon as you have this kind of thing, I mean, in my previous example also I put the H like this, but as soon as you have some loop behavior, And as soon as your DG category has some infinite dimensional home space, any construction software existing adds infinitely many of such arrows. But our construction doesn't matter how this looks like, if there is loop or what, it doesn't matter. In any case, if you have 3 arrows here, you have something like 3 arrows. You add 3 arrows there. If you have infinitely countable many arrows here, you add countable many arrows here. The complexity doesn't change when you construct cylinder. But whereas in other construction, even if you have 3 arrows here, but if there's this loop behavior, you have to add infinitely many arrows. That's the so.
Can I ask one question, Doğancan? So,
Sure.
that cylinder construction that you have drawn here reminded me of cobordism category of topological quantum field theory, kind like cobordism morphisms kind of thing. So, is there some? Can we define some sort of TQFT for DG categories kind of thing?
I don't have direct answer for that. But it makes sense that this corresponds to some type of cobordism.
Yeah,
Because it is basically an identification of this category with this category.
right.
The goal of this cylinder is, I mean, even topology, what does this cylinder does? It connects this circle to this circle by its copy. It's like a map.
Yeah.
Like a map. This also like that. Actually, this identifies this with that in a way, these arrows.
So, I mean, the total that diagram with the categories, is there something called DG2 category kind of thing?
I think there is in a Legendrian contact homology setting, but to be honest, I didn't read them. I know such papers exist, and I think they do this kind of things, but they don't use what it's the cobordism is not this.
I see.
Their cobordism is maybe yes.
Some
I
complex
should not say
analytic.
much thing because I don't know, but I assume it's not this. And even if they define something like this, they still had to add infinitely many arrows.
I see.
Okay, you can think like this. You can think this as a natural transformation,
Right,
if you like.
right.
So it's like an infinite natural transformation. This my other result. Unfortunately, I didn't have time to say, but this looks like an infinite natural transformation between identity functors.
Right.
But infinite natural transformation, again, as I said, has arrows, infinitely many arrows. For each composable arrow, you add the arrow.
Right.
It's not like, so, I mean, usual natural transformation is this. There's no arrow you add. This is very strict. But we cannot deal with usual natural transformation. We need to have infinite natural transformation, which adds arrow for each composable morphism. Let's say if this H, G and F composable, so you add some arrow for that. You have G, F, H, then you add arrow for them. And since if there is an a loop, there are infinitely many composable arrows, and then you add infinitely many arrows like that. And that, yeah, infinite natural, if with this language, if you think this is an infinite natural transformation, yeah, you can think is a cobordism between functors though, not DG categories.
Right.
So this is like a functor, identity functor, which sends DG category itself, so its images itself, and it's also identity functor. And it's a infinite natural transformation between two identity functor. And actually, this is related to Hoshit homology, if people know. Hoshit homology is given by infinite natural transformation between identity functors. But anyway, so maybe that's not your question, but
Thank you. So I
insert it
guess
there.
in the chat box there is Thank you. Yeah. So any
Okay.
more questions or comments? So then let's take Doğancan once more. And we thank him because he gave his seminar very late at night in Tokyo. So thank you
No
very much.
problem. I thank you because you stayed 20 more minutes.
No, that's fine. I mean,
Thank you very much for that.
yeah. So I'm now closing the recording.